In 1926, a French inventor filed a patent that shook the agricultural world. He claimed one simple device placed at the edge of a field and connected to the soil with a wire could triple crop yields. No fertilizer, no machinery, no fuel. Just a wire pulling electricity from the open sky. Official photographs showed peas growing 7 to 9 feet tall in June, cabbages twice their normal size, grapes sweeter than anything the farmers had tasted. Government committees in Britain secretly documented the results for 18 years. And then, almost overnight, the research vanished. The inventor's name was nearly erased from the record, and a method that cost almost nothing disappeared just as a new industry worth billions was rising to take its place. Today we're going to follow that story from beginning to end. The science, the inventor, the evidence, the disappearance, and what you can do in your own garden right now with a piece of copper wire and 30 minutes of your time. Stay with this video, because the final scene is the one that matters most. If you are a gardener who believes that the most powerful tools are often the ones that cost the least, and that the most important knowledge is often the kind that gets quietly set aside, then you are in the right place. Subscribe to Seedly and ring the notification bell. Every week we go deeper than the product shelves and the trending hacks into the methods, the history, and the science that has shaped how food actually grows. Now let us go back to France, back to 1920. His name was Justin Christofleau, French engineer, inventor, and stubborn believer in the invisible. In the years following World War I, as France struggled to rebuild its farms and feed its people, Christofleau was working quietly on an idea that most of his contemporaries considered eccentric at best. He believed that the atmosphere itself was alive with electrical energy, not lightning, not voltage in any dangerous sense, but a slow, constant, measurable electrical field that exists between the ground beneath our feet and the sky above our heads. And he believed that plants, which already lived and grew at the boundary of that field, could be made to grow with extraordinary vigor if that field was amplified and directed. He called his device the electromagnetic terreau celeste. Farmers in the wine-growing regions of Lacue, Yvelines, Montfort-l'Amaury, and Gambès tested his apparatus on their fields and vineyards between 1922 and 1927. They reported doubling and sometimes tripling their harvests, larger vegetables, sweeter fruit, faster germination, and crucially, a dramatically reduced need for chemical fertilizers even during prolonged droughts. The Brisbane Daily Mail on October 10, 1926, ran coverage of the device, noting a possible answer to world crop shrinkage. Christofleau filed patent CH118648A, documenting the invention formally. The patent still exists in the Swiss Patent Archive. You can read it today. His apparatus placed a small metal box at the top of a pole. Flexible metal antennae radiated from a central vertical rod to capture atmospheric electricity. A galvanized wire carried the collected energy down the pole and into the soil. The whole device worked passively. No power source, no batteries, no engine. It used wind, vibration, temperature changes, sun, frost, and humidity to generate what Christofleau called an electric depot in the soil. And the soil charged by this depot appeared to feed plants in a way that nothing else could explain. What happened next is one of the more remarkable footnotes in modern agricultural history. The British government quietly established the Electroculture Committee in 1918 under the Ministry of Agriculture, not as a fringe investigation, as an official body with funding, field trials, and reporting obligations. They ran experiments for nearly 18 years, from 1918 through 1936. Members of Parliament mentioned the committee in Hansard, the official parliamentary record, as early as 1924, referencing government investment in electrical stimulation for agricultural use. Interim reports documented crop improvements in controlled trials. The science was being taken seriously at the highest levels. Then, with very little public explanation, the committee was dissolved. Its findings were filed away, and the research conducted over nearly 2 decades with government resources was never acted upon. Historians who have examined this record note that the timeline aligns almost precisely with the rapid expansion of the synthetic chemical fertilizer industry in Britain and across Europe. That alignment is worth holding in your mind as we move forward. Now, let us set aside the history for a moment and talk about what is actually happening in the atmosphere above your garden right now. Because, this is not speculation. This is physics that Richard Feynman taught in his famous lectures at Caltech. Under normal fair weather conditions, there is a measurable vertical electric field near the Earth's surface of approximately 100 volts per meter. That means the air 1 meter above the ground carries 100 volts of potential difference relative to the ground itself. At 10 meters up, the field is roughly 1,000 volts. This field exists because the Earth's surface carries a net negative electrical charge and the upper atmosphere carries a net positive charge. The two are separated by the air between them, which acts as a partial insulator. But the air is not a perfect insulator. There is always a slow current flowing. Ions in the air, created by cosmic rays and radioactive decay from the soil, allow this current to move constantly and quietly through the atmosphere. Peer-reviewed research by atmospheric physicist Professor Giles Harrison of the University of Reading, published in the Journal of Electrostatics in 2018, documented this fair-weather atmospheric electric field in precise detail and noted its biological implications. Because living organisms, including plants, exist within this field and have evolved in its presence for hundreds of millions of years. Plants are not passive objects sitting in this electrical environment. They are biological conductors. Their cell walls carry electrical charge. Their root systems interact with the charge gradient in the soil. Their internal chemistry, the signaling that moves through a plant at speeds that cannot be explained by chemistry alone, appears to involve bioelectric pathways. Research on plant electrophysiology has confirmed that plants use electrical signals to coordinate responses to wounding, pest attack, drought, and light changes. These signals travel through the plant the way nerve impulses travel through animal tissue. Not identical, but analogous. And if that is the case, then a device that amplifies the ambient electrical field in the soil around a plant's roots is not a fantasy. It is, at minimum, a coherent hypothesis about a real biological mechanism. To understand why electroculture disappeared, you need to understand what arrived at almost exactly the same time: the Haber-Bosch process. Developed in Germany in the early 20th century, this industrial method of fixing atmospheric nitrogen into ammonia made it possible to produce synthetic nitrogen fertilizer at massive scale for the first time. By the 1920s and 30s, the fertilizer industry was rapidly expanding across Europe and North America. Governments that had previously funded agricultural alternatives, including electroculture, began shifting investment toward this new industrial model. The model was simple, powerful, and enormously profitable. Grow dependency. Sell inputs. Repeat each season. A method that required a farmer to buy nothing after the initial installation of a copper wire and post represented no ongoing revenue stream. It could not be sold in a bag. It could not be patented by a corporation season after season. It asked for nothing beyond the patient gardener's time and a piece of wire. When a zero-cost passive method competes with a multi-billion-dollar input industry, the passive method rarely wins in the policy room, regardless of the field results. Christophileu's work was not disproven in any formal scientific sense. There was no landmark study that replicated his conditions rigorously and found nothing. The research simply stopped being funded. The committee dissolved. The records were filed. And a method that had been producing documented results in government trials for nearly 2 decades vanished from the institutional record. That is not dramatic conspiracy. It is simply the ordinary, quiet institutional drift away from anything that does not serve the prevailing economic model. And it happened slowly enough that most people never noticed it happening. So, what would happen to a plant if you genuinely increased the electrical field strength around its root zone? Let us think through the biology. Plants absorb water and nutrients through their roots via a process that involves, in part, electrical charge differences between the root surface and the surrounding soil solution. Ions in soil water carry charge. Positively charged nutrient ions like calcium, magnesium, and potassium are drawn toward negatively charged root surfaces. If the overall charge gradient in the soil is amplified even slightly, the movement of these ions toward roots becomes more efficient. Uptake improves without the plant expending additional metabolic energy. The second mechanism involves soil microbiome activation. Many of the beneficial bacteria that drive the nitrogen cycle, the phosphorus cycle, and the decomposition of organic matter are electrochemically active. Research on electrically active biofilms, communities of bacteria that conduct electricity through the soil, has confirmed that these organisms respond to changes in ambient electrical potential. An increase in the soil's electric field may selectively favor the activity of these beneficial organisms. Third, plant signaling. Research published in journals including Plant Cell and Environment and Frontiers in Plant Science has established that plants use electrical action potentials to coordinate their responses to the environment. A stronger ambient field may enhance the efficiency of these internal communication systems. None of this is proven at the scale that the most enthusiastic electroculture advocates claim. The honest scientific position is this: the mechanisms are plausible, the early evidence is intriguing, the formal trials are inadequate in number and rigor, and the question is genuinely open, which, for a method that costs almost nothing and harms nothing, makes it one of the more interesting experiments a careful gardener can run. Now, let's move from 1920s France to 2018 China, because honestly, this is where the story takes a turn that's a lot harder to dismiss. The South China Morning Post, which is a major international English-language newspaper based in Hong Kong, reported in 2018 on large-scale electroculture experiments conducted by Chinese agricultural researchers. The scale, folks, was unlike anything attempted by Christoflo or that British committee. Researchers actually suspended high-voltage electrical cables over roughly 3,600 hectares of farmland. Not just passive copper spirals. This was high-voltage infrastructure spanning nearly 9,000 acres. The reported results included crop yield increases of up to 30%, and, get this, a reduction in pesticide usage of up to 70% in the treated areas. 30% more food, 70% fewer chemicals, all across an area larger than many small counties. These were not just garden hobbyists posting on social media. This was a nation with strong economic incentives to boost food production efficiently, and a credible international news organization reporting the results. The trial confirmed that, well, something measurable was definitely happening. And the underlying principle that electrical fields influence plant physiology, soil biology, and pest behavior was the very same principle Christoflo had staked his career on nearly a century earlier. Not swayed by hype, not dismissive either, just observant. Before we get to the how-to, I want to spend a moment being honest with you. Because, honestly, the best gardening channel is one that tells you what is true, not just what is exciting. The skeptics of passive electroculture make valid points. A 2025 study published in the journal PLOS One, conducted by researchers at Marquette University in Wisconsin, tested passive copper electroculture directly. They assigned vegetable plants to 3 groups: no copper, exposed copper wire, and buried copper wire, and ran the experiment for 8 weeks. Their conclusion? Passive copper rods did not improve yield in home container vegetable gardening. That is a published, peer-reviewed, controlled study. It deserves respect. Garden science communicators at Washington State University have noted that the evidence base remains inconsistent. The honest position is this: we do not know with certainty that passive electroculture works in a home garden setting. We know the physics is real. We know the history is real. We know the large-scale results are reported and intriguing. We know that the cost and risk of trying it are essentially zero. And we know that gardeners who have tried it report results that range from no change to remarkable improvement. which means the most rational thing a thoughtful gardener can do is exactly what Christo Flo did a century ago. Try it, watch closely, record what you see, and let your own garden be the experiment. Here is the simple passive method you can implement today. What you need: bare copper wire, at least 18 gauge or thicker, uncoated, not plastic covered, bare copper. You need a length of roughly 3 to 4 feet, and a wooden or bamboo stake about 2 feet long to wrap it around. Step 1. Wrap the copper wire in a tight spiral around the stake, starting from one end like a spring. Leave about 6 to 8 inches of wire unwrapped at the bottom. Step 2. Before you insert it, orient it toward magnetic north. This is the detail that separates intentional electroculture from simply sticking copper in the ground. Christo Flo specified that his apparatus be aligned with the Earth's magnetic field. Use a compass. Find magnetic north. Orient the stake so the spiral faces that direction. Step 3. Drive the stake into the soil at the edge of your bed or between plants. Push it in until the bare, unwrapped wire at the bottom is fully underground, making contact with the soil. The spiral extends upward above the soil surface into the open air. This is your antenna. It captures the ambient atmospheric electrical field. It conducts it down through the copper and deposits it into the soil at the base. Step 4. Observe. Do not move it. Give it a full growing season. Check the soil nearby weekly. Look for changes in texture, worm activity, and moisture retention. Compare treated beds to untreated beds if you can. Document what you see. Across the internet and in gardening communities, reports from home electroculture practitioners have surged since 2022. The results are not uniform. Some gardeners report no visible change after a full season. Others describe increased worm activity in the soil around the copper stake within weeks. Faster seed germination, stronger root systems visible at transplanting. Taller, denser vegetable growth on the treated side of a split bed. One long-term experiment tracked blueberry production over 2 full seasons with copper spirals installed. The gardener noted that established bushes sent out runners and new plants within months of installation, something not seen in 4 previous years on the same property. The Washington Post noted in 2024 that for every gardener who swears by electroculture, another is ready to debunk it. That polarization tells you something useful. Not that one side is right and the other wrong, but that the outcomes are genuinely variable. Soil type, climate, existing biology, bed orientation, plant species, these factors likely determine whether passive electroculture produces a measurable effect in any given garden, which makes it all the more important that you run your own trial under your own conditions, rather than relying on anyone else's result as your answer. Let me step back from the copper wire for a moment, because the story of electroculture is not just a story about whether a spiral of copper can increase your tomato yield. It is a story about how knowledge moves through the world, about what happens to methods that threaten existing economic,